happy to announce that today's talk is from Professor Arjen Dondorp, who is an intensive care and infectious disease physician from the Netherlands. Since 2001, he is based at MORU, which is Mahidol Oxford Tropical Medicine Research Unit in Bangkok, Thailand, where he is deputy director and heads the Malaria Research Department. He is a professor of tropical medicine at University of Oxford, visiting professor of clinical tropical medicine at Mahidol University in Thailand, and a fellow of the Academy of Medical Sciences in the UK. His main research interest includes the pathophysiology and treatment of severe malaria, anti-malarial drug resistance, new treatments for drug resistance, falciparum malaria, and the improvement of intensive care practice in the developing countries. He leads a large research program on the development of triple artemisinin-based combination therapies for the treatment of multidrug resistance falciparum malaria. Professor Dondorp currently chairs the Regional Steering Committee of Regional Artemisinin Resistance Initiative from the Global Fund. This is a large regional grant supporting the malaria elimination effort in the Greater Mekong sub-region in the Southeast Asia. And he is a well-known figure in the field and has published over 450 papers in peer-reviewed journals. So with this, I know this is a very short introduction for him. I can talk for a day about his introduction, but without wasting any more time, I request Professor Arjen to start his talk. Welcome, Professor Arjen, and over to you.
Yeah, thank you very much for that nice introduction, which was already way too long, I think. And it's an honor to be invited for this lecture series. And so I've been asked to give a presentation on the current situation of anti-malarial drug resistance in falciparum malaria. And I will focus, of course, mainly on artemisinin resistance, because the whole world depends on the artemisinin-based combination therapies for the treatment of falciparum malaria. So a first slide is to show that, of course, it's not a new phenomenon, anti-malarial drug resistance. We've seen it in the past. Somehow it always emerges in low transmission settings, especially in Southeast Asia and especially in Cambodia. I'll come back to that a bit later. And we've seen that in the past with chloroquine resistance, which was first detected in the Greater Mekong sub-region of Southeast Asia in the late 50s already. And then spread from there westwards. It reached India in around 1980. It skipped the ocean, and then when it arrived in Africa, it had devastating effects, because, as you all know, the majority of falciparum malaria is harbored in sub-Saharan Africa. We've seen a similar pattern with fansidar sulfadoxine pyrimethamine resistance. So pyrimethamine resistance again emerged first in the Greater Mekong sub-region, and then spread westwards and crossed the ocean into the African continent. So why is it that it always starts first in a low transmission setting? There are several reasons for that. An important reason is that in low transmission settings, the infection rate is much lower. So, for instance, in the endemic areas in India, a child is bitten maybe once a year by an infected Anopheles mosquito. Whereas in sub-Saharan Africa, in high transmission setting, can be daily infected bites. And because of that, the infections in Africa are almost always multiclonal, so multiple strains at any moment when someone develops malaria. And because of that, there's a lot of genetic diversity in the infection. And then during the sexual stage of the parasite in the mosquito, if there is a resistant parasite, it can lose its resistant genetic makeup quite easily because of this crossing over of the genes between the different strains. And then the parasites will lose their resistance genes. Another reason is that in high transmission settings, a much larger population is asymptomatic because a child acquires semi-immunity, pre-immunity during the, say, first 5 years of their lives. And if you go to schoolyards in, say, Uganda, up to half of the children can be carrying parasites without being ill. So they will not seek treatment. And therefore, on the parasite population as a whole, the drug pressure will be much less. And the drug pressure is less anyway in these areas of high transmission, because if there was real good full coverage, then there would not be so much malaria around. So the drug pressure is lower. In fact, I'm always a bit surprised when you see those numbers from treatment coverage with ACTs from African countries, which is often around 30% or so. And then another important reason is immunity. So again, in sub-Saharan Africa, children develop pre-immunity against the parasites, so that helps to clear the parasitemia. So if the parasite is a little bit resistant to the drug, the infection can still be cured by the human host. So those resistant parasites, if it's not full resistance, they cannot propagate to the mosquito and the next child. So those are important reasons why there is a barrier to the development of resistance in Africa, but that is not an absolute barrier, as we have seen in the past with chloroquine and sulfadoxine pyrimethamine. In addition, there seems to be a transcontinental barrier in the Anopheles mosquito, that African Anopheles species are a little bit reluctant to take up Asian Plasmodium falciparum, but also that is not absolute. So several reasons. The next slide is just to stress the fact how important antimalarial drug resistance is and how devastating its effects can be. And it's not even that easy to find actual numbers about that, but when chloroquine resistance arrived in Africa and spread there, and it arrived first in Eastern Africa, and it was rampant in the 1990s, during a time when chloroquine was still very widely used for the treatment of falciparum malaria. In the 90s, we saw an increase in the malaria deaths in that area, whereas in Western Africa, where chloroquine resistance was much less prominent, we saw a decline because of a better health system. So in fact, it has been estimated that millions of African children might have died because of chloroquine-resistant falciparum malaria. Also in the Greater Mekong subregion in Southeast Asia, where artemisinin resistance and ACT failure is now a problem. In the areas where we had ACT failure and that ACT was still the first-line treatment, we could clearly see an increase in malaria, falciparum malaria transmission. So it is really important. So in the 90s, it was not only a problem in Africa with chloroquine resistance and sulfadoxine pyrimethamine failure, but the problem was even worse in the Greater Mekong subregion. This is an example from the Myanmar-Thai border, where where chloroquine was lost as an effective treatment. Sulfadoxine pyrimethamine was lost. Quinine, not full resistance, but was also becoming a little bit less effective. And quinine for uncomplicated malaria is an awful treatment anyway because of all the side effects and the 7-day treatment. Mefloquine was introduced, also rapidly lost, also at the higher dose. And then we were really saved by the artemisinin drugs. So artemisinins developed in China, coming from this plant, Artemisia annua, with this very particular chemical structure, with this peroxide bridge here, which is very reactive. Very potent drugs, killing all the stages of the erythrocytic cycle. So not only the more mature stages, trophozoite and schizons, as with quinine and all the other antimalarials, there's also these earlier ring stages. It's gametocytocidal, so very good drugs, but they have a very short half-life. So plasma half-life of around 1 hour. So after 5-6 hours, all the drug has disappeared. So with a 3-day treatment, even if you have a very potent drug, then as the artemisinin, you still have a couple of hundreds or thousands parasites left, which then need to be mopped up by another drug. And that's why artemisinin combination therapies were developed and deployed, where the partner drug can be less potent, but with a longer plasma half-life, and it varies in between the different partners, to mop up those remaining parasites. So these are the 6 ACTs that are currently recommended by the WHO. They are the first line treatments for falciparum malaria in all the endemic countries. Since 2006, prominent in the malaria treatment guidelines from the WHO. And really they have made a big change. They have really contributed to a decline in the malaria burden in Africa, but also in Asia. So we really depend on these ACTs at the moment. So that's why it was quite a shock when it was noticed now over 10 years ago in Western Cambodia again, that the potency of the artemisinin drugs had declined. So this high potency, where every 48-hour erythrocytic cycle of the parasite 10 to the 4th decline in parasitemia every cycle, that 10 to the 4th, 10,000 times decrease in parasitemia was now only 100 times decrease in parasitemia in resistant parasites. And you see that here on the left-hand side. So this is the very rapid decline in parasitemia in sensitive parasites at that time, at the Thai-Myanmar border. And the much flatter slope here you see in Western Cambodia in 2008-2009, with only every 48 hours 100-fold decline in parasitemia. So that was worrying for several reasons. I come back to that later. And after that, a very good molecular marker for artemisinin resistance was discovered by the Pasteur group, which were mutations in the CALCH gene on chromosome 13 of the Plasmodium falciparum in the so-called propeller region. And these single nucleotide polymorphisms, it was always only one of these SNPs were detected in resistant parasites. So apparently the parasite only allows for one SNP, otherwise apparently the parasite is not viable. But there were more than 75 of these SNPs detected in the CALCH gene. And a lot of them have been now directly linked to the slow clearance phenotype. This, what you saw on the left-hand side. And also have in transgenic parasites in the laboratory, it has been shown that just introducing that CALCH mutant makes those parasites more resistant to the artemisinin drugs. So that's very handy to have a molecular marker, because then you can do surveillance in the laboratory and you don't depend fully on those very labor-intensive clinical studies. So why Western Cambodia always as the start, and now again with artemisinin resistance? So I said in my first slide, it's because it's a low transmission area, but also the drug use was quite poor in Cambodia, but that's also true in other countries in the region. But for instance, in Cambodia, pyrimethamine and chloroquine were added to the salt, which of course give subtherapeutic levels of the drug, and that's a perfect sort of drug pressure to make the parasite resistant. For the artemisinins were used for a long time as monotherapies, not protected by the partner drug. And that was the common deployment in the 1980s and 90s, but also after the introduction of ACTs in the private sector, and you see that here a picture of that. Artemisinins were still often given out in the private little pharmacies or shops as monotherapies. That, by the way, has completely disappeared now also from Cambodia. So several reasons why it is Cambodia where this started. But again, it's not unique to Cambodia. Other countries and also India will have similar problems with drug use. So it has been suggested, in fact, initially that came from India, from Professor Rathod, that maybe there's something else different in Cambodian Plasmodium falciparum parasites, and that there is a special phenotype, which was named the accelerated resistance to multiple drugs phenotype, which was shown in vitro, that these parasites were easier to become resistant to antimalarial drugs in vitro. And there are also other studies now supporting that sort of hypothesis. One is that the parasite needs a genetic backbone, so other mutations in the gene apart from the CALCH mutation, to make this CALCH mutation successful. And that was shown in large genetic epidemiological studies, and you see that here on the left side graph. So mutations in the ferredoxin gene very commonly coincided with the CALCH mutant. And here the MBR2 mutants, apicoplast gene mutation, and a certain CRT mutation. So it's not then just the CALCH, but also this backbone, which is very prevalent in Cambodia. And that's also reflected in these transcriptomic studies, that a whole bunch of genes seem to be upregulated or downregulated in artemisinin resistance Plasmodium parasites. And an important pathway that is upregulated is the so-called unfolded protein response, which is sort of an oxidative stress response by the parasite, which helps the CALCH mutant parasite to resist artemisinins. Artemisinins, with that peroxide bridge, they act through an oxidative mechanism. So biologically this observation also makes sense. And then thirdly, there are observations that the DNA repair genes might be different in these artemisinin-resistant parasites from Cambodia, which fits again with the hypothesis from Rateau that I showed you in the last slide. So several reasons why it always starts in Cambodia, but yeah, we don't completely understand that yet. So back to artemisinin resistance, it is not full resistant to the parasite. It is the early ring stage of the erythrocytic cycle that become resistant to the artemisinins. And that's very nicely shown in vitro, again by the Pasteur group, that if you expose for a few hours small rings to artemisinins and you compare resistant and sensitive parasites, you see a big difference in survival between those two groups of parasites. If you add the artemisinins to more mature parasites, so trophozoite stages, this difference between resistant and sensitive parasites completely disappears. So it is here in the small ring stages that where you notice the resistance. So that means that the artemisinins are still useful in the treatment of falciparum malaria, but you have this much slower clearance of the parasitemia. And we haven't seen this changing over the last 10 years now that we know that there is artemisinin resistance. So it's still this decrease, this sort of 100-fold decrease in killing rates in the parasite, but not full resistance, luckily. But with that, it does affect the efficacy of the artemisinin combination therapies. So the efficacy of the ACT is a composite of the artemisinin components and the partner drug components. You need both to clear the infection. So if you have resistance to the artemisinins, you see a decline in efficacy. This is, as an example, artesunate mefloquine. So if you have artemisinin resistance but not mefloquine resistance, we have a marker for that too, which is MDR1 multiplication. You see in the Thai-Myanmar border this around 20% decline in efficacy. If you have only mefloquine resistance, but still good sensitivity to the artemisinins, you see there's around 7% decline in efficacy. But if you have both, then you see a massive decline in efficacy of around 40%. And that is what happened, in fact, on the Thai-Myanmar border now around 7-8 years ago. So both contribute. That seems obvious, but there is a lot of discussion somehow around this, whether it's the partner drug resistance or artemisinin resistance that is important. Well, both of them contribute to ACT failure. As a side step, that's why I don't like the term ACT resistance, because then you cannot tell whether it's artemisinin resistance, partner drug resistance, or both. I think it's better to talk about ACT efficacy and then say whether it's artemisinin resistant, partner drug resistance, or both. Another example is dihydroartemisinin piperacin, a big problem in the eastern Greater Mekong subregion, including Cambodia. So it's the other way around. If you have only piperacin resistance, you already see around a 20% decrease in efficacy of this ACT. For piperacin resistance, we also have a marker, which is plasmapsin 2 amplification. If you have only artemisinin resistance but sensitivity to piperacin, you only see a little drop in efficacy. We also see that, by the way, with artemether-lumefantrine. But if you have both resistance to the artemisinin component and piperacin, you see a massive decline in efficacy to around only 55%. The right-hand graph explains why that is a bit different with piperacin resistance compared to mefloquine resistance. I won't go into that too deep, but it has to do with the pharmacokinetics of piperacin. So the terminal half-life of that drug is very long, so very slow clearance. And because of that, if you have just a small increase in the IC50, so just a little bit loss of sensitivity, the time of the drug concentration of piperacin above the MIC, so above the inhibitory concentration, that time gets reduced a lot. So it has a big impact then on the efficacy of the piperacin component. So artemisinin resistance is bad for ACT efficacy in complicated falciparum malaria, but we are of course also worried for severe falciparum malaria. After the large trials, the Sequomet and Aquamet trials, we know that IV or IM artesunate is much better in saving lives than quinine. So in adults, 35% decrease in mortality between the two arms, around 22% decrease in mortality in children with severe falciparum malaria. So, but what if artesunate is losing its potency? Well, there are not big studies about that, and that has to do with the fact that severe malaria is becoming very rare, luckily, in the Greater Mekong subregion, because there is very little transmission nowadays there. But there are some observations that patients presenting with severe malaria did not respond well to IV artesunate and either died or rescue treatment with quinine had to be given. That said, there is a recent observational study from southern Vietnam, where we also have a lot of artemisinin resistance, and they do not report an increase in case fatality from severe falciparum malaria with artesunate treatment. So the first bad thing about artemisinin resistance is that it reduces the efficacy of the treatment. The second important consequence is that once you have artemisinin resistance, it's much easier for the parasite to develop resistance to the ACT partner drug. And that is because after a 3-day ACT treatment, usually you have a couple of hundred, couple of thousand parasites left, but after a 3-day treatment in artemisinin resistant infections, you still have 10 to the 5th, 10 to the 6th parasites left that only see the partner drug because of the short half-life of the artemisinin component. So a much higher chance that, because of the much higher number of parasites, that the parasite develops resistance also to the partner drug. And that's not only theory. We have clearly observed that with mefloquine resistance on the Thai-Myanmar border, where artesunate mefloquine was introduced at the time that there was already mefloquine resistance in the 90s, but then the ACT, that's the fat red line, was very effective. So over 90% efficacy for more than 10 years. And then as soon as artemisinin resistance arrived, mefloquine resistance reappeared. We know that from the molecular markers that we have for mefloquine resistance. And then once mefloquine resistance was compiled with artemisinin resistance, then you see a very sharp drop in efficacy of this ACT. So artemisinin resistance facilitates resistance to the ACT partner drug. And once you have ACT failure, then the resistant parasites spread as wildfire. And also there we have clear examples from the Great Mekong sub-region. And it's not only because you have treatment failure, so the parasite comes back, the resistant parasite comes back and then is infecting a new patient again. It's also because there's an amplification in that process, because recrudescent infections always have higher gametocytemia and more frequent gametocytemia. Not only for ACT failures, after ACT failures, but also with mefloquine, fansidar and chloroquine. So that increases, amplifies the transmission, and then you get a larger reservoir of resistant parasite, more clinical cases, more deaths in the end. That will lead to more drug use, of course, and we only have the ACTs at the moment. So even more drug pressure on the parasites, and you have this amplification cycle. I'll show you later on, we have seen that happening with DHA piperacin failure in So the third reason artemisinin resistance is bad, so reduced efficacy, facilitates partner drug resistance. Also, artemisinin resistant parasites are probably in itself more transmissible. In observations we had during our trials, we saw that artemisinin resistant infections before recrudescence already had higher gametocyte numbers. We know from transcriptomic studies that artemisinin resistant parasites have an upregulation of this AP2G gene, which predilects the parasite to become a gametocyte. And we also now know from in vitro studies that the male gametocytes in artemisinin resistant parasites, those are the red curves here, are more resistant to artemisinins, both artesunate and dihydroartemisinin. And because, as I said at the beginning, the artemisinins are also gametocytocidal, but less so in the artemisinin resistant parasites. So 3 reasons why artemisinin resistance is bad. Once you have artemisinin and partner drug failure, you see rapid spread, and we observed that in Cambodia. So first we had this multitude of CALT mutants that confers artemisinin resistance. In Cambodia, we saw a single lineage carrying this C580Y CALT mutation very rapidly spreading throughout Cambodia. And it really took over the whole parasite population in the course of a couple of years, as you can see here in this graph. So this whole orange part is the C580Y single lineage parasite, which we know when we look at the haplotype of this parasite taking over. And in its course, it picked up piperacin resistance. That's why it spread so quickly. That's a different lineage as we observed in the Western Great Mekong sub-region, which is sort of divided from the east because there's a corridor with almost no malaria in the middle. Here another C580Y strain or lineage spread, and also this 446I lineage spread in Myanmar. And this is where we are at the moment in Cambodia. So with the spread of artemisinin resistance compounded by piperacin resistance, we see this massive reduction in efficacy to very low levels here in northeastern Thailand, in Western Cambodia, and in southern Vietnam, which is the red line, which has prompted to move away from DHA piperacin as the first-line treatment in these countries to a different ACT. And this is where we are at the moment in the Greater Mekong sub-region. So in Cambodia, 4 out of the 6 ACTs reduced efficacy, 3 out of 6 in Thailand, and Laos, 2 out of 6 in Vietnam. Surprisingly, artemether-lumefantrine which is the first-line treatment in Laos, PDR, has held up quite good. Although we see a bit of reduction in efficacy to around 90% efficacy, which is the WHO threshold to change to a different ACT. What about India? Well, India does epidemiological surveys, of course, looking at the KELCH mutations. They are reported in low frequencies in big surveys in Tripura and Assam. But then there was this publication from a few years ago now from West Bengal, where they also reported these KELP mutant infections with slow clearance, with the slow clearance phenotype. And these were the KELP mutants that were found, the 446I, the 539T, which they said that patients had traveled from Cambodia and these other two. However, follow-up studies, and we did a trial together with you in Midnapur in West Bengal, and we did not see these KELP mutations coming back. We did see again these KELP mutants, but they were in very low frequencies, so they were not selected for, which makes it much less worrying. So artemisinin resistance, as we know at the moment in India, is not a big problem yet, but of course we have to be very vigilant and keep on having close surveillance that this is not happening in the near future. What about Africa? Well, Africa harbors more than 90% or even 94% of the falciparum, Plasmodium falciparum burden. So we are very worried if artemisinin resistance would arrive there. So surveillance studies there are also taking place, and until recently we only found KELP mutants in a very low proportion of parasites. A bit what you could expect as the background mutation rate of the KELP gene, so around 1%, sometimes 2%. And you could expect that on the level of how well the KELP gene is conserved in Plasmodium. I won't explain that graph on the left-hand side, but you can sort of see that KELP is quite conserved as a gene. It means that if you have a mutation, if the parasite allows that mutation, or that the parasite cannot live with a mutation like that, from that you can derive the sort of background mutation rates that you can pick up by chance. But then more recently, both in Rwanda and Uganda, and maybe also in Ethiopia, Eritrea, KELP mutant infections have been detected, and they are expanding in those countries. So the best well documented are parasites from Rwanda, carrying this KELP mutant 561H, and more recently also from Uganda, the 675V and 469Y mutations. And these have not spread from Southeast Asia, and you can know that from the genetic analysis. They have the genes around the KELS mutations are different from Southeast Asia. So the haplotype is very different. It has really emerged locally and then spread from there. The Uganda artemisinin resistant Plasmodium falciparum will be published soon. The Rwanda problem has been extensively published now, both in Nature Medicine and in Lancet Infectious Diseases. And there you see this map that the mutation, this 561H mutation, has really expanded in parts of Rwanda till 20%, even a bit more, of the parasite population. And they show the slower clearance. They have this common genetic background, so it's really local spread, and the parasite is establishing itself in the parasite population. Luckily, artemisinin, which is the first-line treatment, is still very efficacious there. But as I said earlier, there's now more stress on the lumefantrine partner drug. So lumefantrine now becomes more vulnerable to also develop resistance. So that's something to keep really a close eye on, because once you have ACT failure in Africa, we are very afraid the same scenario will happen again as we saw in the past with chloroquine resistance. Last example, South America. There, the 580Y KELS mutant parasite was detected around 5 years ago, as you see here in the graph, and here in Guyana. There, this resistant parasite did not manage to establish itself. It sort of disappeared again there. So maybe it lacked this genetic backbone. Maybe genetic uptake was lost during recombination because there was a bit higher transmission with more genetic diversity. As we know from in vitro studies, as such, there is fitness loss cost in parasite carrying the 580Y mutation. So this is, in a nutshell, the global situation of artemisinin and partner drug resistance at the moment. By the way, Ido Warren is collecting all these global data and putting them in maps on their website, which is very important for policymakers. So surveillance of drug resistance is very, very important. And there are several ways to do that. There are, of course, the WHO-led therapeutic efficacy studies, which are sort of the reference standard for that. So very important, but also quite labor intensive. It's going to be difficult to do them in very low transmission areas like the Greater Mekong subregion. Just you don't have enough patients to include in the studies. You can look at in vitro sensitivity, which is also good, but quite difficult to do in some places, and not always that straightforward what it says about the in vivo efficacy. And then there are the molecular markers, which is a great tool to do surveillance on antimalarial drug resistance. For some important drugs, we do not have molecular markers, for instance, lumefantrine or pyronaridin. But there is quite a good list now of drugs where we have good molecular markers, and I've listed them there here. So we have marks for chloroquine resistance, mefloquine, sulfonamides, pyrimethamine, cycloguanil, atovaquone, the artemisinins, and piperacin. So a great tool to do drug resistance surveillance. Okay, so with artemisinin resistance now really established in Southeast Asia and now also starting in Africa, what is the response to that? We need new drugs. We need non-artemisinin based combinations, or we need other potent drugs to be added to them. And there is a good pipeline of new compounds that are being tested, and this is from the website of MMV, so the Medicines for Malaria venture, who coordinates globally the development of new antimalarials. But then this development, even a drug that is quite far already in phase 2 studies, or sometimes even phase 3 studies, can still then fail and be taken off the list of drugs that are being developed. Examples, for instance, artefenomol, OZ439, a synthetic endoperoxide drug, for years under development, I think at least 15 years. Last year it was decided not to develop it further because of several problems with the drug. DSM-265 and MMV-048 are other examples that last year they were still quite prominent on the list. Now they disappeared. These two drugs are still very promising and in phase 2 and phase 3 trials. The spiroindolones, or KE609, cipargamin is the brand name. Very potent drug, as potent as, or even a bit more potent as the artemisinins, very rapid parasite clearance, and the imidazolopiperazine, KF156, or ganaplacide, as the brand name for that, also potent, attacking multiple stages of the parasite. So if they will be deployed, it will of course be in combination therapies to protect them against resistance. And from ganaplacide we know from Novartis that it will be combined with lumefantrine, probably in a new formulation of lumefantrine that can be dosed once daily. But these new drugs, it will take, most people think, another 5 years or so before they can come to the market. Whereas we now currently have this problem of artemisinin resistance and ACT failure in some parts of the world. So what do we do at this moment? We can only use the drugs that we have available now. So there are several approaches. You can deploy the antimalarials, the artemisinin combination drugs, as triple artemisinin combinations, where you choose the partner drug in such a way that they have different mechanism of actions and ideally also different resistance mechanisms. And we do not have that much choice what we can combine. But we are currently testing artesunate piperacin plus mefloquine and artemethylumefantrine plus amodiaquine added to it. And another group is testing artesunate pyraneuridine atovaquone perguanil. And then lastly, we have also been testing arterolane, which is a synthetic endoperoxide piperacin plus mefloquine. And these drugs, so the bigger trials have been done with the first two triple ACTs or TACTs that I mentioned earlier, and they are still very efficacious also in multidrug resistant infections, and they are safe and reasonably well tolerated. Other approaches are that you extend the duration of your ACT treatments. It's in theory a possibility, has not been really tested yet. It's safe to do. We know that from studies from Myanmar and DRC Congo. If that also is more efficacious, maybe, but trials needs to be done. You can do drug rotation, which is in fact the strategy at the moment in the Greater Mekong subregion. So you deploy an ACT as a first-line treatment. You wait till efficacy drops below a threshold of 90%, and then you move to your next ACT. In practice, that has been shown to be difficult in the field. For instance, in Cambodia, the move away from DHA piperacin to artesunate mefloquine took 2 to 3 years. So programmatically, that has been shown to be quite difficult. Same example from Vietnam. And also in theory, then it's just waiting for the next ACT to fail. Whereas in the triple ACTs, those partner drugs, they can protect each other, which you would also get if you give sequential use of first one ACT and then the second ACT. The half-life of those partner drugs are long, as I showed you before. So then you also get that dual protection. But this sequential use also has not been trialed yet in the field. Theoretical disadvantage is that you extend the duration of your treatment from 3 to 6 days, and then adherence could get worse. The last few slides are about these triple ACT treatments. Here you see in a graph why it is good to give 2 partner drugs that can protect each other. And I said it in words already earlier. In artemisin-resistant parasites, you have a much higher parasite burden left after the 3 days of ACT treatment. If you have a single partner drug, then this whole bunch of parasites only sees the single partner drug, so it's very prone to develop then resistance to the partner drug. Whereas if you give 2 partner drugs, they can mutually protect each other because they both remain above the MIC concentration for the duration of the infection till all the parasites are being killed. And this is at the moment the most advanced triple ACT, artemether-lumefantrine plus amodiaquine. Currently we use it in our trials as a co-package formulation, so in one box, but the blisters are separate. This will now be developed as a fixed dose combination, which of course needs when you really think about deploying this triple ACT in real life. I think especially for the Eastern Greater Mekong subregion, this is quite a good option as a next step for the treatment of uncomplicated falciparum malaria. But it might also become an important combination for Africa now that artemisinin resistance has arrived there. Not only for efficacy, but also to protect the partner drug, especially lumefantrine, from developing resistance if you keep on deploying artemether-lumefantrine as an ACT rather than a triple combination. So then I come to my last slide. So in summary, it has been mainly about artemisinin resistance, this presentation, which is bad because it reduces the efficacy of the ACTs, it facilitates the development of partner drug resistance, and it increases the transmissibility of falciparum malaria. It's still an evolving picture. We have to be very vigilant doing our surveillance, especially also in India. In the Eastern Greater Mekong subregion of Southeast Asia, we see this high failure rates with certain ACTs. So there we already see this next step happening. And we hope that this same scenario will not repeat itself in Africa, where artemisinin resistance has now also been very clearly documented. But it's not only doom and gloom. In the Eastern GMS, malaria elimination is going very well. So Cambodia, Laos, Vietnam, the cases per year is in the thousands only. So it's really going well. So that's, I think, one of the reasons it hasn't spread from there. And we hope that falciparum malaria really will be eliminated there with all the efforts that's going in there over the next few years. And until we have the new antimalarials available, we have the triple ACTs that can buy us time for now, since they are still efficacious and also shown to be safe and reasonably well tolerated. Thank you very much for your attention. I cannot hear you. I think you're muted.
Can you hear me now?
Yes.
Yes. So thank you very much for your insightful drug resistance system in malaria, and despite we are doing good towards malaria elimination, but this is a drug resistance is still serious threat for us, and we are really thankful for you to you consider a request for sharing your wonderful work with us. So, I mean, we have some queries, if you can see here in the chat box. So if you allow, may I take some of the queries from here?
Of course, yeah. I cannot read them myself, sharing myself.
I can read that. Okay, so one of the query is, according to the analysis, which one is the predominant K13 mutation in India? And is this mutation is common in all the selected countries or regions? Is K13 mutation is also associated with Vivax malaria?
Yes, so those are all good questions. So in India, there's not a single CALS mutation that is really more prevalent than the other one. This 446 mutation is seen once in a while. 580Y seeing once in a while, but not clearly being selected for and expanding. And this one study from the New England now a few years ago, so this was the 446I and especially also this 539T CALS mutation, has not really been identified after that. So there's not a single CALS that is really popping out in India. In Africa, it is this 561H in Rwanda and the 675B in and all these CALS mutations, they have a slightly different fitness loss if you look at them in vitro, and probably together with the genetic backbone makes which one is the most successful to spread. In Vivax malaria, you also have a CALS gene in Plasmodium vivax. And some countries, they treat their Vivax malaria with an ACT rather than with chloroquine. We haven't seen clear evidence yet of artemisinin resistance in Vivax malaria.
Okay. One of the question is low selection of artemisinin resistance strain in India due to adherence to ACT, and why GMS is the main source of drug resistance strains.
Yeah, so that first point is very important. I think I forgot to mention that. Of course, if there is little adherence to the 3-day course of an ACT, that is also a recipe for inducing resistance in the parasite. And it happens quite easily because they are such effective drugs. The patient often feels well again on the second or third day and then is not inclined to complete the treatment course. Yeah, that is also an important driver of resistance. Why it always happens first in Cambodia, I think I went into that quite extensively in my talk. Several factors, it's low transmission. There was artemisinin monotherapy for a long time in the 80s and the 90s. But maybe there are additional parasite factors that make, especially why we don't really know, Cambodian parasite more vulnerable for resistance. We have some clue about it on this DNA repair mechanisms, this in vitro observation from Professor Arjen that parasites from Cambodia, it's easier to induce resistance in them, and the genetic backbone and the transcriptomic profile of Cambodian parasites.
Okay, next is, could addition of multiple pharmacophore moieties onto a single molecule be used as an alternative?
I don't fully understand that question. I think it refers to, oh yeah, I see that there are efforts for that too, that you not give two drugs separately, but you construct a single molecule that has different modes of action with combining two classes of compounds into a single molecule. Yes, that can, of course, be a very nice approach, which it is being tried at the moment, but will take quite some time to develop still.
Okay. One is, in a preclinical in vivo model of experimental cerebral malaria, rosiglitazone improved survival over artesunate alone, and what is the mechanism?
Yeah, rosiglitazone, that is now, that will be trialed in African children with severe malaria. It's not because of its effects on the parasites, but because of its immunomodulatory action that it has. It works in an animal model. I think we really have to wait and see if that is also translates to a benefit in humans, in real patients. So too early to say.
So the last one is, will addition of antimalarials with long half-life generate resistance to even ACTs?
So long half-life drugs, as a general statement, are more vulnerable to the development of resistance because they have in the blood, they have long tail ends where the concentration of the drugs reduces, and then there comes a point where that concentration still kills the sensitive parasites, but not those few resistant parasites that float around, and then the resistant parasites can escape and multiply. So that is why combining two of those together, where you make sure that you match the pharmacokinetics of those partner drugs are similar and with similar potency, then those two partner drugs can protect each other. Because if a parasite is resistant to one of those two, it will still be killed by the other partner drug.
Okay, if your time allows, may I take 2-3 more?
Of course.
Yeah, so one of this is, could you elaborate on the relationship between CALCH mutation and oxidative stress in the parasite?
Yes, that is a very good question, but also a difficult one to answer in short period of time. So the observation is that in CALCH mutant parasites, the genes that are involved in this oxidative stress response, unfolded protein response, are upregulated. How that is on a genetic molecular basis is quite complicated, and there are some hypotheses about that. But how those gene expressions are all linked in some way is quite complicated.
Okay, this is a slightly broader question. How much it is a problem for Vivex?
Yeah, so in 5X malaria, we have clearly documented chloroquine resistance, of course, in 5X malaria, especially in Papua New Guinea, Papua Indonesia, and some other places in Indonesia. So artemisinin resistance in 5X malaria has not been very clearly documented yet. But also that we need, of course, surveillance that will not happen.
Okay, another one is, do surveillance of background mutations may act as hints of inclination towards low ACT efficacy?
Yeah, this genetic backbone. So first of all, it is important. So we, at the moment, for the surveillance of artemisinin resistance, we really focus on the CALCH gene and look for mutations there. In theory, artemisinin resistance can also develop through a different pathway, and then you do not pick it up because you only look at your CALCH gene. So in that respect, it is important to, but that has to be more focused studies to also look at other genes, including this genetic backbone. This genetic backbone is quite nicely shown for the Greater Mekong subregion. It's not to be said that is also the required backbone in other areas in the world. For instance, the artemisinin-resistant parasites in Rwanda, the 561H CALCH mutation, they're not associated with these additional backbone mutations we see in the GMS. So it's a different genetic backbone there.
Okay, so I mean, I can see a few more, but I think it's. Should I take one or two more, or?
It's completely up to you.
Okay, okay. So I'll take the final one. Would you thus rather suggest, when conducting genome-wide resistance mapping studies, whole genome sequencing and analysis is performed to be thorough?
What is exactly the question there?
Would you thus rather suggest, when conducting genome-wide resistance mapping studies, whole genome sequencing and analysis is performed to be thorough?
Yeah, so sequencing the whole genome of Plasmodium falciparum is becoming cheaper and cheaper and quicker. So we can have that data more and more easily, and I know India is also doing those studies. Then the next step is the bioinformatics. You have massive amounts of data on all these genes and gene mutation. So that is difficult, and I think the capacity to do those analyses is maybe less widely available than the sequencing itself. So that should have a real emphasis in the future. Methods for that, there are, of course, they have been developed. But they will also still evolve over time to become better and better.
Okay, so with this, I think we will close this session here, and thank you very much again. And I request the unanswered question can be sent to us or can be sent to Professor Arjen directly. And thank you very much for considering our request. With this, I would like to announce one more thing here, that on the coming Friday we'll have Professor Elizabeth Winsler from School of Medicine from UCSD, and she will talk on the malaria drug accelerators. And this lecture will start at 10 a.m. next Friday here. So I request all the audience, including Professor Arjen, to please join us. Thank you very much.
Thank you.
Thank you very much.
Thank you very much. It was my pleasure.
Thank you.